Model rocket launch. The phases of a model rocket launch include the thrust phase, the coast phase, and the descent phase. So during the thrust phase, you have ignition and liftoff, and that indicates the start of the thrust phase. The end of the thrust phase is when the propellant in the motor has been expended. During this phase, the rocket is accelerating upwards due to the thrust provided by the rocket motor. The forces acting on the rocket in this phase are thrust, it's an upward force, gravity is a downward force, drag, in this example, is going to be a downward force, and lift. You will only have a lift force if the rocket is not moving straight up. So that is something we will discuss a bit later. The second phase is the coast phase. The coast phase starts when the thrust phase ends, and during the coast phase, the only force acting on the rocket is gravity and drag. There is no longer any thrust because the propellant in the motor has been expended. Shortly after the rocket reaches its maximum height, the ejection charge within the rocket will cause a parachute to deploy, and the rocket will descend under the force of gravity. Drag will now work in the upward direction. Okay, and so that process of the rocket descending is called the descent phase. So looking at this diagram, this would be the thrust phase, this would be the coast phase, and this would be the descent phase from 4 to 5. Anatomy of a model rocket. Okay, so for this particular rocket, you have a nose cone, you have the body tube, you have a shoulder, you have a body tube again of a different diameter than this body tube, then you have a bow tail, and finally you have another body tube whose diameter is equal to this diameter. And then of course you have the fins. The rockets we will design in this class will not have shoulders or bow tails. They'll just be one single body tube with a constant diameter. Forces on a rocket. The thrust force is upwards. The gravitational force is downwards. Since these model rockets will be launched near the surface of the Earth, we can use m times g for the gravitational force. The lift force L acts perpendicular to this axis of symmetry, and it is 0 as long as the angle of attack is equal to 0. And I'll talk a bit about what the angle of attack is when we get to a rocket launched with a horizontal disturbance such as wind. And then you've got drag. For the rocket going up, the drag is in this direction down. Two important quantities. One is something called the center pressure, and it is on average the location of where the aerodynamic forces act on the rocket. Okay. Then we have the center of gravity, where gravity acts on average. Throughout this book and throughout my presentation of model rocket launches, I'll use these three terms: axis of symmetry, longitudinal axis, and roll axis, and it's all the same axis. And it's this axis that runs through the bottom of the rocket, parallel to the body tube, through the nose cone of the rocket. The rocket I use throughout this book to demonstrate and teach rocket aerodynamics is a rocket called the Big Bertha rocket. It's made by the Estes company. And here are some relevant parameters related to the Big Bertha rocket. This is with the C6-5 motor. Its mass is 45.1 grams, the average velocity 38.5 meters per second, and this is with drag. The body tube diameter, okay, here's the body tube. Its diameter is 0.0416 meters. Cross-section area is 0.0014 meters squared. The length of this rocket is 0.607 meters. Drag coefficient 0.56. And then we have several parameters here which are a little bit more complicated, so I'm going to skip these for now. And so the next parameter here, which is a little bit less complex, is something called the location of the center of gravity. Okay, so that's typically a little bit further below center, although it depends on the rocket. Here it's at 0.368 meters, and that's measured from the top. So here's the origin of that coordinate system. So 0.368 meters down. The CP location, the center of pressure, is below that at 0.441 meters. Something called the stability margin, which is really important, of 1.77 is unitless. Then you have the moment of inertia. Remember the moment of inertia, which explains how the mass is distributed about the rotation axis. And the axis I'm talking about here is something called the yaw axis, which goes through the center of gravity. As I said before, the motor that I have installed in this Big Bertha rocket to demonstrate various launch scenarios is C6-5. This is the diameter of the motor, length of the motor. This is the mass of the motor. Here's its average thrust, 4.81 newtons. Here's the thrust duration, 1.83 seconds. And here's the average impulse. Remember, the average impulse is force times time. In this case, it's thrust times time, so it's 8.8 newton seconds. So just this times this. Okay, so we start this section on rocket aerodynamics with the simplest rocket launch scenario, and that's without air. Okay, so this is unrealistic because there is an atmosphere on Earth. But the launch of a rocket in air creates additional complexities such as drag and lift force. So it's best to master the physics and math of this simplest scenario first. Okay, so this image here provides the forces on the rocket. This is actually traveling through air. Okay, so when we're traveling through air, we're going to have drag force, and we also have normal and lift force. But for this first scenario where there isn't any air, we're only going to have to deal with the gravitational force and the thrust force. Okay, we're going to be interested in computing several important quantities related to a rocket launch, including these quantities. Okay, we're going to want to compute its maximum height. We're going to want to compute the velocity of burnout. Remember, that's the velocity at the end of the thrust phase, the total flight time, the energy lost to drag, motor power, and there are others. Okay, so during the thrust phase, there are two forces acting on this rocket. And again, we're launching this rocket without air. So you've got thrust up and gravity down. And here's the equation. So plus thrust, right, minus mass times g, that's the gravitational force on the rocket, is equal to ma, right? This is Newton's second law. The subscript t here means just the mass of the rocket during the thrust phase, okay? The mass of the rocket changes because as it expends fuel, right, it becomes lighter. Okay, so m sub t is the average mass of the rocket during the thrust phase. Okay, so plugging in some numbers, the average thrust for the C6-5 motor is 4.81 newtons. The mass of this rocket during the thrust phase is 0.0628 kilograms, and G is 9.8. All right, and that's going to be equal to M times A. Okay, I have one equation and one unknown here, so we can divide both sides by 0.0628 kilograms, and we get 66.79 meters per second squared. Okay, so if we divide that by 9.8, we get 6.8 Gs. So that's a lot. It's quite a bit of acceleration. A reminder here is that when you guys build your own rocket and or do problems related to homework, you're going to have to remember that the mass is typically given by the rocket manufacturers are in grams, and our force equations need to use kilograms, right? We're using standard units. Okay, so you have to convert these masses to kilograms. Okay, so let's continue with the thrust phase. What's the velocity of the rocket at the end of the thrust phase? And this is given the term velocity of burnout. Okay, so remember this equation. It's a constant acceleration equation. All right, so we're going to use the velocity at the end of the thrust phase is equal to the initial velocity. Okay, this is just the velocity of the rocket on the launch pad, so that's 0, plus acceleration times time. So I am assuming that the thrust force is constant. Okay, it's not constant. It actually varies a bit, and we'll get into that. But um, I am going to use the average. Okay, that's the average force during the thrust phase. Um, okay, so that's what I did here. All right, so I used the average force here, and I solved for basically what the average acceleration is. Okay, so that's what I'm going to input here in for A, and I'm going to solve for V here. V final here is my velocity of burnout. All right, so 66.79 is the acceleration from the previous page times the duration of the acceleration, 1.83 seconds, and that's 122.23 meters per second. So that's how fast this rocket's moving after 1.83 seconds of thrust. So that's like almost 400 feet per second. And when you launch these things, you can't even see them during the first few seconds of the launch. So how high did it go? So remember this equation? This is this provides for the final position given some initial position, given some initial velocity, and given some initial acceleration. All right, so the initial location, and we can say the launch pad is 0. Initial velocity, of course, is 0. It only is accelerating. So we're going to plug the acceleration rate, which we've previously computed, as well as the duration of the thrust here for these two variables, and compute it, and we get 111.84 meters. Okay, so that's how high the rocket has gone just in those first 1.83 seconds. Design considerations. Okay, so design is something you will be doing in this class. You're going to design your own rocket, and so you'll always want to keep in mind how should you go about designing the rocket. So let's just say your objective is to design a rocket that will go as high as possible. So what does this equation tell you um, about how you might want to do that? If you want to maximize d sub f, right, and this is just during the thrust phase, you want to maximize acceleration, right? You also want to maximize the duration of the thrust. Okay. All right. So that seems pretty obvious, right? The bigger this will get bigger with A and T. Okay. So how do you go about maximizing the acceleration? So what I did was I solved this net force equation during the thrust phase for acceleration, and I got this right here. Okay, so to maximize acceleration, you want to maximize thrust, right? And you want to minimize the mass of the rocket. All right. So conclude, to maximize how high a rocket will go, you want to maximize thrust. You want to maximize the duration of the thrust, and you want to minimize the mass of the rocket. So translation, a really tiny rocket with a really big motor. Okay, so the next phase is the coast phase. And here is the net force equation for the coast phase. Okay, so again, we're launching this rocket without air. So after the motor has been expended, right, the propellant has been expended, you no longer have a thrust force, so all you have is the gravitational force. Okay, so the net force on the rocket at such point is just mg, minus because gravity is down. Okay, so if we divide both sides by mass, we get an acceleration of the rocket of minus 9.8 meters per second squared. Now realize the velocity of the rocket is upwards, right? It was moving at 122 meters per second after the thrust phase. So even though it's accelerating down, the velocity is still up, still moving up. Okay, so what we want to compute at this time is we need to know the duration of the coast phase in order to figure out the additional height gained by the rocket during the coast phase. We need to figure out how long it's been traveling during the coast phase. All right, so we're going to use this equation, constant acceleration equation. V final, so that's going to be the velocity when it hits apogee. Okay, apogee just means the maximum height. This was the velocity at the end of the thrust phase. Okay, and then here's our acceleration due to gravity, minus 9.8 t. Okay, we're going to solve for t, and that gives us 12.47 seconds. Okay, so now we can find the total height um, that the rocket flew to. And we'll use this equation again. So D initial is the location of the rocket after the thrust phase. Okay, we've already computed that. Plus the velocity of the rocket at the end of the thrust phase. That's 122.23. And then 1/2 AT squared, so only acceleration due to gravity here. And we know the coast phase is going to last for 12.47 seconds, which is what we just computed over here. So plug that all in, and we get a height of the rocket of 874.09 meters. Okay. So if you were launching this thing on the moon, right, on the moon, there's no air, it would go 874.09 meters. Okay. So what about the time it took to get to the maximum height? It can be computed as follows. The duration of the thrust phase was just um, the duration of the motor thrust, right? That's given by the rocket at 1.83 seconds. The duration of the coast phase, we just computed at 12.47 seconds. So the time to get to its maximum height, 14.30 seconds. Okay, so time to return to Earth. Since there is no air and thus no drag, there is no such thing as a terminal velocity for the launch. So the rocket will fall at a rate of acceleration of 9.8 meters per second squared. So the rocket will fall 874 meters, which was the maximum height of the rocket. The time for the rocket to fall this distance can be derived from this equation here. Okay, and what we're going to do is we're going to say the ground is 0. All right, D final 0. The maximum height 874 meters. Right at the maximum height, there was no velocity. Right, it came to a stop, but it is accelerating downwards. So minus 9.8 is our acceleration, and we're going to solve for t. Okay, so subtract 874 from both sides, multiply both sides by 2, divide both sides by 9.8, and take the square root, and that gives you 13.3 seconds. So the total time of this rocket in the air, time to the top, 14.3, time on the way down, 13.3, so 27.6 seconds. Okay, so this is the program called Open Rocket, and I've loaded the Big Bertha rocket. This is what it looks like. And I'm going to run the scenario with the C6-5 motor with no air. Okay, so I'm going to go to Motors and Configuration, make sure I've got the right motor. There we go, C6-5. Then we go to Flight Simulations, and I've already got a lot of these set up with C6-5, no air. All right, so we're going to edit that simulation. Okay, so here's the key. Make sure that's unchecked and make sure you have air pressure to 0. Okay, so that's no air. Then we're going to hit Simulate and Plot. Okay, and I'm going to have on my y-axis altitude and vertical velocity. Okay, I'm going to get rid of vertical acceleration for now. And on the x-axis, I'm going to have time. And you can add, here's all the stuff you can add. And there are going to be all sorts of scenarios. Actually, not that many scenarios. I usually just stick with vertical velocity, vertical acceleration and altitude, also angle of attack. Will be a scenario where you want to run the angle of attack, and then time on the x-axis. Okay, so let's go ahead and plot that. All right, and there you have it. So let's take a look at this graph in detail. The blue line is the vertical velocity, and the red line is the altitude. So here is the thrust phase from here at launch, okay, where the velocity is 0, to here where the velocity is at its maximum, okay? When the velocity is at its maximum, it's called the velocity of burnout, and that denotes the end of the thrust phase and the start of the coast phase. So here is the coast phase from the time of burnout until the time that the rocket reaches its maximum height, right here. Okay, and at such time, the velocity of the rocket at the top is 0. Okay, and the descent phase is from the point where the rocket is at its maximum height until it returns to the ground. Okay, here's a little bit different graph. Here we have vertical acceleration in blue and vertical velocity in red. So you can see that the vertical acceleration spikes, drops, and remains pretty constant. So when the vertical acceleration goes from this point here to down here, you know you're at the end of the thrust phase. Acceleration now is minus 9.8, right? At the end of the thrust phase, the only acceleration you have is gravity. At the end of the thrust phase, when you have your maximum velocity. At the end of the thrust phase, until the rocket returns to the ground, the velocity drops linearly. A very useful theorem in the analysis of rocket launches is the impulse momentum theorem. If you recall, the mathematical equation is this. Force times the time over which the force is applied is equal to mv final minus mv initial. If you recall, this is the final momentum, this is the initial momentum. So this theorem tells us that the greater the impulse, the greater the final momentum. So an 8 Newton second impulse motor will provide more momentum than a 6 Newton second impulse motor. Example, if only the force of the motor was acting on the Big Bertha rocket, the velocity of the rocket at the end of the thrust duration would be given by the formula below. This is simply impulse divided by mass, right? Impulse divided by mass, the initial velocity is 0. So that'll give you the velocity at the end of the thrust phase. So plugging in the mass of the Big Bertha, 0.0682 kilograms, and the impulse of the C6-5 motor, 8.8 Newton seconds, gives us a velocity of 129.03 meters per second. So this number is not the same as the velocity of burnout computed previously, which is 122.23 meters per second. And this is due to the fact that the impulse on the rocket due to gravity, which is about 1/7 of that of the impulse from the motor, was not considered. But you can see that the greater the impulse of the rocket motor, the greater the velocity of burnout. So when you're shopping for rocket motors, first of all, you want to make sure the rocket motor fits your rocket. And for any given rocket, there's, I don't know, maybe half a dozen motors that will fit it. If you want maximum height, you want maximum impulse. You don't want to look at just thrust alone, right? Because say you have a thrust of 5 newtons. A 5 impulse motor would be 5 newtons for 1 second. A 10 impulse motor would be that same 5 newtons of thrust times 2 seconds, or 10 Newton seconds of impulse. So again, you want to really be focused on impulse and not just thrust when shopping for motors. Computation of work, energy, and power of the Big Bertha launch. So the work done on the rocket by the C6-5 motor during the thrust phase is force, or thrust, times the displacement of the rocket during the thrust phase, which was 111.84, times the cosine of the angle between the force vector and the displacement vector. They're moving in the same direction, so the angle is 0. Okay, this product gives you 537.95 joules. If you recall, average power is equal to work divided by time. So the work done on the rocket by the C6-5 motor was 537.95 joules, and we divide that by the time over which the thrust was applied, which was 1.83 seconds, gives us an average power of 293.96 watts. Okay, the work done on the rocket by gravity during the thrust phase is, we use the same formula here, but this time the force is due to gravity. That's just mg. Again, the displacement's the same. It's 111.84 meters. And this time the angle is 180. Okay, because the displacement of the rocket is up, but gravity is down. Okay, so plug this into your calculator and you get minus 68.83 joules. So what this is telling us is that during the thrust phase, gravity has done negative work on the rocket. The net work done on the rocket during the thrust phase is the sum of the work done by gravity and the work done by the thrust of the motor. The work done by the thrust of the motor was 537.95 plus, and then the work done by gravity on the rocket was minus 68.83. So you add those up and you get 469.12 joules. The change in the kinetic energy is equal to the net work done on the rocket. Okay, and the net work includes both gravity and thrust. We can compute the kinetic energy of the rocket after the thrust phase by using the work kinetic energy theorem. If you recall, the kinetic energy is given by 1/2 times the mass times velocity squared. So the net work done on the rocket is previously computed, 469.12. We're going to plug that in over here to this equation. and that's equal to the change in kinetic energy. The initial kinetic energy while sitting on the launch pad was 0. So 1/2 times the mass of the rocket during the thrust phase, 0.0628, times velocity final squared. We're going to solve for this velocity. We're going to multiply both sides by 2, divide both sides by 0.0628, and take the square root of both sides. And that gives us a velocity at the end of the thrust phase of 122.23 meters per second. And this is the same result computed previously using the net force equations. Okay, here is your assignment. Compute the following for the Big Bertha rocket using the B6-4 motor. It's a little less powerful than the C6-5 motor used in the previous examples. You need to provide the computation details. Also provide the open rocket graph of the simulation. Include the variables vertical velocity and altitude on the y-axis and time on the x-axis. So you'll compute acceleration during the thrust phase, acceleration during the coast phase, velocity at burnout, height after the coast phase, time to the maximum height, power of the motor, kinetic energy of the rocket at the end of the thrust phase, momentum of the rocket at the end of the thrust phase. And here are the parameters for the B6-4 motor.